Today's goal is to prove Menger's theorem, and then mention a couple variants of it. I think I'll just give one proof. There's two proofs in the book. The second proof is of a more general form, which I will state. But the proof of that is kind of similar to the third case in the proof we're going to give. So I don't know if I'm going to have time anyway to cover it. But I'm actually going to change the notes and introduce a different proof entirely. So you may want to read that later because it's like a cool different technique. I just made, like, it's a last minute change. Okay, anyway, so we got to start off with the definition. It's still in red. Okay, so let's take a pair of non-adjacent vertices. So for non-adjacent vertices, U and V, in some graph G, a UV separator. We've kind of hinted at a term like this before. We didn't use this one exactly. Is a vertex set, say X, such that U and V are in different components after we remove X from G. So they're distinct from each other. Okay, so such that U and V are in different components in G minus X. Okay, that's a very natural way to think about what it means to separate two vertices. Okay, so you have, like, a separator definitely disconnects your graph because I'm talking about you have different components. It doesn't mean it's the smallest way to disconnect your graph. It's just a way that guarantees U and V are in different components of the resulting graph. And actually, to be honest, later on we're going to prefer the following definition here. This one's a little more natural, but it's equivalent to saying the following, that G minus X contains no UV paths, right? That's equivalent to them being in different components, that there's no path between the two of them. When we generalize this definition a little bit later, it will be desirable to think of it in this way, that containing no paths is a little more desirable, but in this simple situation here, it's equivalent to just saying that U and V are in different components. But what does it mean for them to be in different components? It means that there's no path between them. So the two are equivalent. Okay, so I drew an example in the notes, and let me illustrate it again here. What is a separator and what is, say, a minimum separator? So let's say we've got a graph like this. Here's U on this corner and V on this corner. And this doesn't have to be precise. My vertices are, let's just say the vertices are wherever these lines cross each other. It doesn't matter too much. I don't want to have one between U and V though. Right, according to this definition, we're only talking about non-adjacent vertices. I mean, that's necessary, right? If U and V are adjacent, then there's no UV separator. You can't get them in separate components, because I'm not talking about destroying edges, I'm talking about destroying vertices. So in this picture, for instance, if I were to destroy all these vertices here, just by simple examination, you can see this is a separator. I think I called it X. So it's a separator X. But there's better ones, right? I could destroy these two vertices here. This is a minimal separator. Go and say it's X prime. And down here, I think I have 3 vertices. I don't know. Is that 1, 2, 3, 4 maybe? Or there's even better. Here's a 2 separator if I destroy those two. I don't know, like this is one vertex and this is one vertex, something like this. Okay, so there's separators, there are minimal separators. There's a bunch of other separators I can find in this graph too. Any way of just splitting those two across, right? All the paths kind of pass through, like geometrically, you can confirm that I'd separated it here. You don't really need to think much about graph theory. Okay, and so Menger's theorem, it will ultimately be about connectivity, about K connectivity. When I get to the end here, first it's going to be this min-max statement, which doesn't directly talk about connectivity. However, if you think about this for a second, the size of the separator has definitely something to do with connectivity, because connectivity, if you're K connected, it would mean that the smallest separator out there among all pairs of vertices would be of size K. Now, it doesn't mean every pair of vertices has a separator that's as small as size K. It just means that there is a pair of vertices who have a small separator somewhere. So there is a connection, but this is talking about separators here is actually a more general statement than talking about connectivity, I suppose. Okay, so the first version of Menger's theorem I want to give several versions because if you look up Menger's theorem online or in books or whatever, you're going to get, there's 3 or 4 different versions, and all of these are simultaneously usually called Menger's theorem. So Menger's theorem. This is from like, I think maybe 1927 or something like this. This is an ancient theorem in graph theory. Basically, this predates graph theory, in fact. We'll see why that is a little bit later on. And I would put this, like, this is in this category, and we'll return to this, but there's like 6 theorems in graph theory that are all equivalent to each other that look wildly different. And we'll see several of them, and we'll prove some of the equivalences of them as well. But they're these like deep underlying facts, and actually they go beyond graph theory, what they're claiming as well. But they happen to be equivalent to each other. And the first that we'll see in this class is Menger's theorem. Other classes start with maybe Hall's theorem, things like that. And not all of them, but many are of this min-max type. So what Menger's theorem claims is that some minimal structure in the graph is equal to some other maximal structure. So they balance each other out, is maybe one way of saying it. Okay, so if we start with U and V are non-adjacent vertices in a graph G, then the size of a minimum UV separator. Okay, so there are many UV separators in principle, but there are minimum size ones. So the size of a minimal size separator is equal to the maximum number. Okay, actually we already defined this. Maximum number of internally disjoint UV paths. So these two quantities are equivalent for every single vertex. You have this equality. It's not equal across vertices, right? 2 other vertices might have 3 internally disjoint paths, and their minimum separator would be of size 3, while some other pair of vertices might have 5 internally disjoint paths, and their minimum separator would be of size 5. Okay, but I can claim this for every single pair of vertices simultaneously, that you have this equality here. And if you take the minimum across all of those things, that will be your connectivity. I don't want to say too much because applying Menger's theorem here to get that stronger statement, what we call Whitney's theorem, will be your first homework exercise on this new set here. It's not that hard, but it's translate this into a global property about connectivity. Okay, so is this clear? I mean, if we look at the picture up here, maybe we can confirm that here. We found just through examination that we had a separator of size 2 here. And so it means that there should be 2 internally disjoint paths and no more. I'm not going to prove it, but actually if you look here, certainly you can find 2 without much difficulty, right? I mean, the easiest is just go like this and go like this, right? There's 2 there. And you notice they both cross over the separator here and here. And actually that already gives us part of the proof here, right? I'm claiming that these 2 are equal to each other. I'm going to prove equality in my favorite way, is showing this one is greater than or equal to this one, and then this one is greater than or equal to this one, right? Our standard strategy. One direction is immediate. So let's write that one down, and we see it in the picture even there. So proof. Okay, so U and V are already specified. There's just going to be arbitrary non-adjacent vertices in there, and let's let K be the size of a minimum UV separator. So we have some quantity to refer to. So K is the size of the minimum separator. In the example above, K equals 2. Okay, so first of all, let's observe that you definitely can't have more than K internally disjoint paths. Okay, so clearly there are at most K internally disjoint UV paths. Can someone tell me why? We can like, let's imagine here's U and here's V, and this is a separator here. Why can't we have more and there's K vertices here. Why can't I have more than K internally disjoint paths? What is an internally disjoint path, or just a UV path's relationship with X?
So any path has to intersect that separator.
Exactly, right? Any path from U to V goes through the separator, because actually using the second definition, after removing this separator, there remains no UV path. Or in other words, the graph is there's U and V are in separate components. So like there's no path that escapes that set there. Otherwise it wouldn't be a separator. So every UV path passes through there. And if I want a collection of internally disjoint UV paths, then each of those internally disjoint paths uses at least one of these vertices. Maybe I have some bad ones that are actually like using 2, right? But they can't use 0. So each path of an internally disjoint collection, not among all paths, there may be way more than k paths, but internally disjoint ones, I can only get up to k. There's no way I'm getting more than k because each one uses one vertex of the separator, okay? So I'll just say as each uses at least one vertex of x, our separator x. Well, okay, let's not even say of x because there might be other separators. So of a min separator. Actually, it uses them of any separator, but if we talk about the minimum one, we get an upper bound. So what remains to prove then is actually we just need to find k internally disjoint paths, and then we're done. Okay, so it's enough to find k internally disjoint UV paths. We've used internally disjoint last time, but some books call this independent. So internally disjoint paths are independent paths. Just so you're aware. I don't prefer this term because independence has other meanings. Okay, so first we want to rule out a couple of cases here. We're going to do induction on the number of edges, but I want to rule out the cases when k equals 0 and k equals 1 first, because when I have a separator that I'm working with, I want it to have at least 2 vertices in it. Otherwise, my arguments don't work. But fortunately, these are both immediate. So if k equals 0, it means that the separator between u and v is 0. So what does that actually mean in the first place? So what's the meaning of having a UV separator of size 0? Minimum 1. There's already no UV path. I need to destroy 0 vertices to destroy all UV paths. So this means that there are 0 internally disjoint paths, which is equal to the size of the minimum separator. So there's nothing to prove. It's instantaneous. Like here, I don't even need to do less than or equal to, greater than or equal to. It's equal. There's 0 and 0. We're done. And actually, when k equals 1, the same thing happens. When k equals 1, then I need 1 vertex to destroy all UV paths. But the graph is connected, right? Otherwise, well, actually, the graph isn't necessarily connected, right? I mean, there might be other vertices that are disjointed, not joined by paths. Actually, let's maybe state that here. Right, this doesn't make any claim about connectivity of the graph. This is a local property for a pair of vertices. How many edges? I mean, how many paths do they have between them? What's the size of the separator? But if the minimum number of vertices you need to destroy all the paths is 1, then there was 1 path to begin with, and there's not 2 for the same reason we observed up here. Each one of them, each path between u and v uses the 1 vertex on the separator, so we get 1 path there. The issue is, with k equals 2 and beyond, is we can't just say, oh, well, you have 1 path for each of the vertices in the separator. I mean, I don't know that, right? I know that there was at least 1, but all the other ones, maybe I only have 1 and it like eats up all the vertices of the separator or something like that. I mean, that suggests that I don't need all k of those, but I don't know, okay? So k equals 0, k equals 1 are done instantaneously. It gets more tricky when k is larger. So assume k is at least 2. Okay, so our minimum separator has at least 2 distinct vertices in it, which will be important in the proof cases here. Okay, so now we proceed by induction on a number of edges, which I'll name m, although we won't really use it here. Okay, so the base case is actually when m equals 0. You could do m equals 1 if you want, then you just have to check a couple of cases. Although it's not that interesting. It's basically the same as m equals 0. So when you have m equals 0, every single separator in your graph for any pair of vertices uv is 0, and there are 0 paths. I mean, it actually just is covered by this case here already, right? It's just true for all vertices simultaneously. Easy. Well, that's what I'll say there, okay? All separators, so yeah, separators size 0, well, minimum separators. Yeah, let's just keep in mind, minimum separators. There are other separators that are bigger. You can just like add whatever you want to a separator always. It's like, yeah, anyway, minimum separator size 0 and no paths at all. So both these quantities are 0 for u and v. Okay, So now, so let's let the graph actually have an edge. So suppose, oh, we don't even use that property right away, do we? Okay, yeah, okay. So suppose m is greater than 0, and statement holds for all graphs with at most m-1 edges. Okay, we won't necessarily be using the same number of vertices. Okay, just we have all graphs with fewer edges. So we're think of how this induction goes. Actually, induction in graph theory, I mean, you guys have already done a couple of proofs with it. It's incredibly powerful. Like, think about the inductive hypothesis that I'm making here, right? I'm not claiming that that this holds for one graph that looks like the graph I'm started with an edge removed. I'm claiming that I'm trying to prove this theorem for graphs with 1,000,000 vertices edges, and I know it holds for every single graph that ever existed with one less than 1,000,000 edges. I mean, there's infinitely many graphs of that type, right? Because I could have as many vertices as I want. So this is an incredibly strong claim, but it's fair. I mean, you can do this with induction as long as I can conclude what I want, that the graph with m edges, regardless of the number of vertices, satisfies the theorem. Okay, so this is very valuable, and also just to emphasize here, this is how you want to do inductive proofs, right? I'm talking about induction a lot in my discrete math class, and in your first discrete math class, how do inductive proofs look like? You have 1 plus 2 plus 3 plus 4 up to plus n equals n times n plus 1 over 2. The inductive hypothesis is just with n minus 1s on both sides, and you have this equation that's nice, and you just add stuff to both sides, manipulate, and you get your solution. Graph theory usually work in reverse, right? You don't start with the inductive hypothesis and say, oh, add an edge to that graph and we're done, because like, you don't know what happens. You rather start with the graph you're trying to prove it for, remove an edge, remove a vertex, remove something, contract, and say, hey, oh, this is a graph, and this is in my smaller family of things. Apply induction to that, and then reconstruct from that thing you got. You can't start with the graph, because in general, you don't know how to build a bigger graph from a smaller graph. Like, it's hard to predict it, okay? So the strategy here will be, I'm gonna have a graph. I mean, we already have a graph, G, with vertices U and V, and their minimum separator is K, and I'm gonna remove an edge from it, or some edges from it, and you apply induction to that graph, and then derive from there. Okay, so there's 3 cases. They're all pretty simple, but after we throw out the first 2 cases, the third case, like what we get is like lovely. It's really cool what falls out. Okay, so case 1 is the cases are distinguished by what the separator looks like. So let me draw a picture in each case and then just describe in words here. So this is G. We've got U here. We've got V here. And there exists a minimum separator. Okay, I'll say that in a moment. That looks like this. So X is the minimum separator, and there's a vertex X in it. And we get really lucky, and there's an edge UX and an edge UV. Maybe there's a separator like that. That's case 1. Okay, so there exists a minimum separator X with vertex X in X, such that UX and VX are edges of the graph. Okay, there could be a separator of this type. Maybe not, but maybe. Okay, so in this case here, I'm going to remove vertex X. So remove X to get the graph G minus X. So that's some new graph, G minus X. Okay. G minus X does have fewer edges, right? Because at the very least, I lost that edge and lost that edge, and I don't get anything else. So I can apply induction to it. But before we do that, let's consider G minus X. So let's make a claim here. So to get G minus X, claim G minus X has minimum separator of size K minus 1 and not smaller. Okay. Why does it have a minimum separator of size K minus 1 and not smaller? Imagine G minus X had a smaller separator. So where's that smaller separator? I can still think of it in this diagram here. Maybe here's the small separator of size K minus 2, right? Wait, what am I trying to say here? Yeah, I'm fine. I'm fine. I'm fine. So this means that in G minus X, every path between U and V was destroyed, right? Except for the one path between using X. That wasn't destroyed, but that's not there in G minus X, right? That's not, doesn't even exist there. So if I have this separator with K minus 2 vertices, oh yeah, Eric, yeah, that's a good question. I should clarify. Eric asks, what do I mean by removing X? I mean the vertex X here. Let me rename these things just to clarify. Yeah, that's very important here. So this is, let me call this vertex here, let's call it Z, okay? So G minus Z, we have a vertex Z such that UZ, VZ, remove X, Z, Z. Okay, so we remove the vertex, we just lose a single vertex, yeah. Yeah, if we remove G, if we removed all of X, then by definition, there would be no UV paths. Like there wouldn't be, the UV separator would be of size 0. Yeah, so if we remove Z here, then you can't have a separator of size smaller than K minus 1, because if you did, then this separator of size K minus 1 union with Z would be a separator of, sorry, if you had one of K minus 2, this unioned with Z would be a separator of size K minus 1 in the original graph G. Because like, look, these destroyed all the paths between U and V that didn't involve Z. And then destroying Z would remove all the remaining paths. Okay, that's what it means to be a separator there. So yeah, otherwise there exists K minus 1 separator in G, but that's a contradiction. The minimum separator in G is K, not K minus 1, okay? Yeah, so it has a minimum separator of size. Actually, I could say at least K minus 1, but I think you'll see that it's actually exactly K minus 1 here. In fact, it's important that it's exactly K minus 1. Let's check here. So yeah, same thing. It's not smaller or bigger. If the minimum separator in G minus Z was of size K, if it was bigger, then the minimum separator in G, just ordinary G, would be K plus 1. Because after removing these K vertices, like I'd still have to, it wouldn't be enough to remove this guy. That's not clear. That's not clear. Okay, someone tell me why my minimum separator is not, in G minus Z is not bigger. So it's not size K as well. Oh, that's easy. Because G minus Z definitely has a separator of size K minus 1, right? I mean, there's one looking right at me. This set here, X minus Z, that's a K minus 1 separator in G minus Z, because I know that that set plus Z separates the original G. So in G minus Z, I only need to remove those guys to separate the two. So there's of size exactly K minus 1. I have one of size K minus 1, and I can't have a smaller one. If I have a smaller one, then G has a smaller one than K, and it doesn't, okay? So G minus Z has a separator of that exact size. And now we apply induction, okay? So now apply induction to G minus Z. Remember, G minus Z definitely has fewer edges because we at least lost the 2 edges incident. So it's valid to apply induction to it. And what does that mean? G minus Z has a minimum separator. So this is minimum I didn't say minimum UV separator. Every separator I talk about today is a UV separator. Is of size K minus 1. So what does the statement of the theorem say? If the minimum UV separator is K minus 1, then what does it give us?
And we have a UV separator of size K minus 2?
No, not that, Brad, right? So we, like, G minus Z is this subgraph of G, and it has fewer edges, and it has a UV separator of size K minus 1. In fact, the minimum size UV separator is of size exactly K minus 1. And remember what Menger's theorem does is it relates the size of a separator and the maximum number of internally disjoint paths. So it says whatever the size of your minimum separator is between those 2 vertices, there's that many paths, internally disjoint paths as well. So this says that there exists actually the maximum, but I don't care that it's the maximum. We can actually find a family, I just mean a collection of K minus 1 internally disjoint UV paths. Right, that's the statement of the theorem. And so we apply induction to G minus Z. So with a UV sep size K minus 1 to actually get a family of K minus 1 internally disjoint paths. Those exist by induction, right? Remember that's what the statement of the theorem is about. Size of minimum separator is size of maximum number of internally disjoint UV paths. Okay, so great. Let me draw the picture again, but the proof is basically done. I mean, case 1 is basically done now. So here was Z. Here was the rest of my set X. Here's U. Here's V. And now in G minus Z, I found somehow K minus 1 internally disjoint paths. I don't know if they involve the separator or not. I mean, they do, but it's not that important. So here's my K minus 1 internally disjoint paths. But I'm looking for K internally disjoint paths in my graph G, but I can also add on this path here. This one is necessarily internally disjoint because the vertex Z was not available to me in the graph G minus Z, right? I couldn't have used that one. So these red paths existed. So these red paths, they're all in their subsets of G minus Z. And I found them by induction, by magic. And I just have to find one more path. And fortunately, because of case 1, my graph is really, really nice. And I just had this green edge and this green edge, so I could add this on. If I didn't have that property, I couldn't add on the edge, right? Because maybe there was some UV path that went through here, and it's like, well, great, I found K minus 1 of them, but the blue one I want to add on isn't internally disjoint. So it was very, very specific that this configuration allowed me to add one more path. If it looked different from that, I wouldn't be able to do that. Okay, so so adding path U, Z, V to these K minus 1 paths gives K internally disjoint UV paths in G, which is what I want. So case 1's done. Okay, let's do case 2 now. There's 3 cases, so case 2 isn't just the otherwise. Case 2. Let me draw the picture here. So case 2 is that my minimum separator looks like this. There's U and there's V. And I can find 2 vertices in here such that U is not adjacent to this one and V is not adjacent to that one there. Okay? Allowing for the possibility those 2 vertices are identical to each other. Okay? I'm going to call these X and Y. I won't name the big separator, so there won't be confusion this time. So there exists a minimum UV separator, S. Usually we use S instead of X anyway, with vertices X, Y in S, such that UX and VY are not edges. Okay. And I should put allowing X to equal Y. So just to visualize, usually what a separator looks like is something like this picture here. You got U, you got V, you got these vertices you remove, and you got all kinds of paths that go through it. But like the U and V might not have anything adjacent to the separator, right? It might take a long time before the in fact, even better, let me just scroll all the way up here. I know it's not a minimum separator, but like look at this separator here. Look at this picture here, right? You got a separator somewhere in the middle of your graph, and then the paths between U and V, and they like travel, and then they reach the separator, and then go to V there. But they could look like this too, right? Removing all the neighbors of V is always a separator. That's always going to be a separator. Maybe not a minimum one, but it's always a separator. Okay. Oh God. Okay, it like snaps back into place. That's fortunate. Okay, so we're in case 2, and we have this nice configuration here. Keep in mind, again, X and Y might be identical to each other, but all I'm asking for is there a vertex of the separator not adjacent to Y, and simultaneously, is there a vertex of the separator, not adjacent to V, and one not adjacent to V, U and V, okay? All right, so in this case, we're gonna create 2 new graphs, which are not actually technically subgraphs of this thing, but they're going to be graphs that are close enough related and they have fewer edges. I want to apply induction, so I need to construct graphs that have fewer edges. And this, the way this is built here, will force that those are smaller. So let me describe the graph here. So construct graph GU as follows. So GU is the collection of all US paths. Okay, I haven't defined a US path. Normally it was a UV, 2 vertices paths. This is U and then a vertex set here. What these are is, this is just every single path whose one end vertex is U and another end vertex is in S, okay? So all paths from, you can say U to a vertex in S, okay? So, I mean, when I defined UV path, like, you can actually define this for vertex sets, but, okay, so it's the collection of all UV paths. So let me draw that part, and then we have to do one more thing here. So here's U, and here's S, right? And so there are certain paths going from here to here. In some sense, it's like the left-hand side of the picture. By the way, these paths aren't necessarily internally disjoint. I'm just taking every single way of getting there. So you definitely can have paths that look like this, but it's every single path, plus the vertices and edges, okay? And a new vertex. So as of now, this is a subgraph of G, right? Here I just took some of the edges and vertices from G that were like on the left-hand side of the picture here. But I also add a new vertex, V prime, that's joined to every vertex in S. So I add this new guy here, V prime, and I join it to everything in S. So this V prime is sort of like a pretend vertex for V, right? It's sort of, but it's not V itself, right? So this graph here, can someone tell me why it's definitely not actually a subgraph of G? Like, it seems like on the face of it, maybe if we're really lucky, this could be G. Like, here's U, and you take all the paths from U to S, and then instead of V, you have V prime, which is joined to everything in S. But why is this definitely different from the graph described in case 2? This property here, V.
Every vertex in S has a path going to V prime. Yeah,
exactly, right? So Dakota points out that in G, I have this condition that there's a pair, V and Y, for which there's no edge, right? That's the case here. But down here, this V prime was joined to everything there. So it's not the same graph, right? It's not the same graph. Like, this thing's a little bit different, okay? But I want to apply induction to this thing here somehow. And at the moment, it doesn't seem like it has fewer edges, right? At the moment, it doesn't seem like it has fewer edges. In fact, if anything, it seems like maybe it has more edges, right? And we need to, so, okay, yeah. So why does GU have fewer edges? Okay, and this takes a little bit of thinking here, because what if, so maybe I won't give all the details here, but let's just imagine one scenario here. Actually, this will actually prove it, but let's pretend for a second we're stuck in the case that seems problematic, and that is that taking all the paths on the left-hand side preserved all the edges on the left-hand side, and on the right-hand side, we actually like added in one more edge. That seems like something that could have happened. That would mean that G looked like as follows. So let me describe this. So what if G looks like, and let's rule this out. So what if G looked like this? It's U and S, and it's all these paths that I drew above. So it's identical to this here, but V looked like this. V was like these ones here, but not this edge here, right? We know that one of them is missing. And so in this case here, it appears that GU has more edges than G, and it actually does, right? This graph here has one fewer edge than this graph here. But this graph here can't be G. It's impossible for G. Does anybody see why? It has something to do with the size of the separator. Is this vertex needed in the separator? Like, what if I just deleted these vertices here? Would that separate U from V? Like, look, V's whole neighborhood is here. So if I deleted those vertices, this thing would be separated. Right? So this is a more general statement. There always has to be a path through every vertex of the separator from U to V. Because if there's not, why would you delete that vertex? Right? Deleting the vertices destroys the paths. So every vertex has got to be used by some path. So what it means in G is that, yeah, it might look like it's got an edge to each one of those, but it's got to pass through this somehow. So maybe it does a bunch of stuff and then passes through there. So, but now look at this G. This G, that has more edges than this thing here because it had to use at least an edge here and an edge here, possibly way more, to get to S here. Whereas this V prime just went to S directly. This had K edges there. This one has K plus 1 edges here, at least, right? In general, it's gonna have a lot more. V is gonna be like a bunch of paths to there, plus a bunch of other stuff, okay? But that one scenario that seems like it could be fewer edges is not possible. Does that make sense there? So GU actually has fewer edges, and it relies very crucially on this fact here, that it didn't look like, if I couldn't guarantee the non-existence of those two, this edge here, then it might have happened that G looked exactly like this, like it literally was this graph. That would be possible, except that this is not allowed. And so it actually has fewer edges. Okay, so think about what are we actually doing? Let me redraw this picture here a little bit more. So what's G look like? In fact, yeah, let me just erase this whole thing here. I'm going to create another graph here in a moment, and then need a bigger eraser. So this is the picture of G again. There's S, and here's U. U's got paths across, and of course it might have duplicate paths. There's U, and here's V. And V does something similar. Okay. And how do I create GU? So GU just preserves everything on the left-hand side, basically, and replaces the entire right-hand side with a new dummy vertex V prime that's just joined up directly to these guys here. Okay, so it throws out all this junk here and just puts in 3 edges. Putting in 3 edges is going to be fewer edges than the junk I had here because of the property given by case 2. I definitely drop by at least 1 edge. Okay, I'll do the same thing for GV. So define GV similarly. Okay, so GV is just the same thing. I take all the paths on the right-hand side and introduce a dummy variable U prime that's joined to everything here. So it's just the left-hand side. Okay, so this would be, this one here was GU, and GV would be keep this stuff here, GV, and introduce the dummy vertex U prime that's joined to these guys here. So I create 2 different graphs. One simulates the left-hand side, one simulates the right-hand side. Okay. Now, the crucial part was what we observed here is that the number of edges in GU and in GV, each of these graphs simultaneously is strictly less than number of edges in G. Okay, that was subtle but important point. So induction, so we can apply induction to GU and GV. If we want to apply induction to them, what do we actually have to observe first? What information do we need in order to apply induction? We need to know the size of the separator, the UV separator in GU and GV. Well, first of all, there's no V in GU and there's no U in GV. But I mean, let's talk about the U prime V separator and the V prime U separator, because those are going to simulate the other separators there. I don't want to spend any more time than just telling you the separators in these new graphs are of the same size. They're of K. They can't be smaller. If I can find in GV a separator that's a separator between U prime and V that's smaller than K, then that would work in the original graph as well. because separator doesn't involve u prime and it doesn't involve v itself. So it would be a set of vertices that separated v from u as well, if it separates v from u prime. Okay, you might have to think about that a little bit more. I want to finish this proof, so I got to move on. But the point is, you still get a k separator. Okay, both have. Okay, let's just think about GU only for now. GU has, so easy, GU has min u v prime separator of size k. So induction tells us that there exists k u v prime separate paths. So internally disjoint paths. And the same thing happens in GV. But that's great because, okay, I got to draw another picture. I can't add on this one. But this, we're gonna have a collection of paths now. So when I apply induction to GU, it finds me paths from U to, I'm gonna write this V prime. They're internally disjoint paths. How do they look? They travel to here and then they go there. They travel to here and then they go there. They travel to here and then they go there. That's what they all look like in GU. In GV, how do they look? They go from V to V prime and they travel here and then they go down here. And then they travel here and then they go here and then they travel here and then they go here. But I'm looking for internally disjoint UV paths in the original graph. But from this illustration here, can you see where they are? Just ignore this vertex and this vertex. They're not part of my original graph. Throw away these edges and just concatenate each red with each blue, right? For each vertex in S, there will be a red path going there, and these are internally disjoint. Same holds for V, right? I'm just like throw away this stuff. I don't need it at all. And then just glue them together in the natural way. There's one way to do it. Every vertex is used, and then I get blue, red are my internally disjoint paths. Okay, so let's jump to case 3. And we'll finish. So case 3. Now, we've ruled out 2 situations, right? We now never have this situation. That was case 1 in any of our separators. And we also don't have this situation here, that there's a missing one here and a missing one here. So what this means actually is every minimum UV separator looks like, there's only 2 scenarios. It either looks like the following, that it's U directly joined to everything, and V is not joined to anything directly. Like there's paths still, but no edges. Or vice versa, that V is adjacent to everything and U is not, okay? Just, if you think about these 2 cases here for a moment that are ruled out, these never happen. So no vertex in here is adjacent to U and V simultaneously, but also, I can't find, there's never a situation, like there's no vertex that's not adjacent to either of them. Because if this vertex was not adjacent to U or V, we'd be in case 2, right? Case 2 was that there. These don't have to be distinct vertices, right? If you have one vertex that's not adjacent to either U or V, that's considered case 2. So case 3, there's no choice but U be adjacent to everything and V be adjacent to nothing, or vice versa, or V is adjacent to everything and U is adjacent to nothing. And this is not only does a separator like this exist, every single separator looks like that, right? Cases 1 and 2 were they existed ones with this. Okay, so this is quite powerful here. In fact, now we don't even need that much about the separator here. So let's just suppose we're in this scenario here, although the same proof works in the reversed. Okay, so let P equals U, X, Y, ... V be a shortest path, shortest UV path. Okay, so X, Y are just the first 2 edges on that path there. Sorry, the first 2 vertices on that path there. How do I know there's even 2 vertices in the middle of this path? And it's just, why wouldn't it be just a path of 3 vertices? How do I know that doesn't happen? Like, I wrote down the path here, start, end, and there's 2 intermediate vertices there. In general, you can't make claims like that, but if this were shorter, it would look like this. It'd be U, X, V. they'd pass through the separator. They'd be so a consequence of this picture here is that u and v don't have a common neighbor. Like I can't simply go u to x to v. Like that's impossible. So I know my path has at least 4 vertices on it, my minimum path here, the shortest path. That's a consequence of being in case 3. Okay, these exist by case 3. What I'm going to do for you in a moment here is find a shorter path. Okay, if I find a shorter path, I have a contradiction. So the point is case 3 can't even happen. We're not going to apply induction in this one. Okay, so claim g minus xy. So xy is an edge, so I do remove it. Has a UV separator of size k. Okay, so removing that edge doesn't reduce the size of the separator. Otherwise, yeah, z, oops. No, it has a separator, sorry, of size. No, okay, I'm saying the wrong stuff here. Okay. I claim that it has a separator of size k, not smaller. So otherwise, it has, so g minus xy. G minus xy has a separator z of size strictly less than k. That's what it means for it to fail there. So there's some separator z. Then z union x and z union y are UV separators in G. Let's scroll up real quick. So if I remove the edge, so the edge, by the way, x is here, and then there's some y here. Okay, so that's along this path here. Actually, it doesn't have to go into the separator. You might have, like, this could be x and y, and then it gets in the separator somehow else. So it doesn't really matter where x and y are. But the point is, if G minus xy has a separator z, then z union x or z union y are a UV separator in G, because this separator z destroyed every single path from u to v that didn't involve the edge xy. Maybe there's some leftover path using the edge xy still. So if I delete x or I delete y, I definitely destroy any potential path that I didn't get with z here. Okay, so these would give UV separators. Now that's not a contradiction yet, because this could be of size k and this could be of size k, and all it says is great, fine. These are just different separators of G. So this does establish that the separator Z is of size greater than or equal to k minus 1, for instance, but I don't care about that. Okay. So now let's draw the picture here. So here, this is Z union Y in G again. So here's G, this is G, and here's U, and here's V. This is a different separator than the original separator X or S or whatever I called it. Now, what do I know about, did I get this wrong here? Yeah. What do I know about separators in this graph here? We're in case 3, not just some separator, but every single separator has the property that either U is adjacent to everything or V is adjacent to everything. I don't know which one in general, but in this case, I do know, okay? If U is adjacent to Y, then this shortest path, P, U, X, Y to V, why did I go to X? I could have gone directly from U to Y, right? That would have been a shorter path. So what it means is U is not, Y is in here, U is not adjacent to Y. That's not possible, otherwise shortest path, or otherwise shorter path. This means that V is adjacent to everything in here, right? It's one or the other. So V is adjacent to everything here. And now I want a contradiction, but what's my contradiction? I don't know, I'm stuck. Let me look at my notes real fast here. We're kind of done here, but I mean, this should be the end of the proof right here. What's the contradiction? Well, I'm looking at this. You guys can, anybody see it? Cameron?
Got a shortest path, and now you found a shorter one. Isn't it?
Well, I mean, yeah, so, oops. So the fact that we didn't get a shorter path, couldn't get a shorter path, establishes that U isn't adjacent to Y. But then instead V could be adjacent to Y. I mean, it has to be adjacent to Y. But this path U, X, Y, V, maybe that was my shortest path. Right now I've figured out that my shortest path is just 4 vertices, but that wasn't a problem according to, I don't know why this pop-up's on the left here. Like this path here, oh my goodness, could have been the 1. Give me 2 seconds here. Oh my God. This implies every, So U is adjacent to X. Oh, yeah. Okay. Yeah, I missed it. I don't know why these are all interfering. Okay, there was one tiny little point and then we're done here. So yeah, I needed both these separators. So before we get to this picture, let's look at the picture here where my separator is Z union X. This was a different separator. Remember, I claimed both this and this were separators. This separator though, remember here's V, or here's U, and here's V. Again, either U is adjacent to everything or V is adjacent to everything. But now look at this. U is adjacent to X by definition. So U is adjacent to everything in here. Okay? So in this picture, U is adjacent to everything X and everything here that's in Z. And in this picture, I established that U is not adjacent to Y, so V must be adjacent to all these vertices here. But now every vertex in Z is adjacent to both U and V, which either is a contradiction in multiple ways. It's either a contradiction because it's a shorter path, or it's a contradiction because this was addressed in case 1 and not case 3, right? This says we're not in case 3. Either one is fine. But the point is U and V are both adjacent to the vertices of Z for 2 different reasons, right? These are 2 different separators. We have to obey the case 3 property that either U or V is adjacent to everything. In this one, U is adjacent to X, therefore it's adjacent to everything. And in this one, U is not adjacent to Y, otherwise we get a shorter path. So V has got to be adjacent to it, and V's got to be adjacent to everything. And those 2 things can't happen simultaneously. Okay? So we can either shorten the path, either guarantee we're not in case 3. And that's the end of the proof there. Okay?